Okay, let's get started. Any question from previous time? So I guess I still do a little bit of a review before review. So last time we finished this teaching about Grover's algorithm. So we have this quite cool Grover lower bound. Okay, so we prove so it's a Grover lower bound, but we say it's really a lower bound on the search problem or the OR problem. Okay, we had the where is it? The lower bound for OR problem. Okay, OR function. So we can think about the decision version of search is the OR of this truth table of your small f. And anyway, so we have this pretty cool lower bound. This lower bound is actually generalized to what we call the adversary method. And so you can see like the first table of this thing we talk about is very general. It doesn't depend on the function we solve. So really, the only thing that depends on the function you try to lower bound is this f0 and f this f and f prime pair, where you pair between the zero input and so if you choose a different pair between the zero input and the one input, then you can lower bound different functions. Okay, but anyway, we use this to lower bound the OR function, and we are able to get square root and lower bound. And this proves that our Grover's algorithm is optimal. Okay. And yeah, then we talk about other things about Grover algorithm, like what if you don't know m, and what if you want zero error, etc. Okay, okay, but a lot of those things will not be in final, and today will be final review. And I don't have too much material prepared, so probably we'll just finish early today. Okay. But anyway, so what will be in final? Okay, so what will be in final? Something in your midterm will still appear in final. Okay, so you still need to remember like a Dirac notation, calculation, and circuit calculation. Okay, and yeah, so because the final, so the second half of the class we talk a lot about algorithms, so obviously still you should remember the circuits. So for example, this was in midterm review, but for example, so this thing here, you should be able to calculate the outcome is beta 0, so basically 0, 0 plus 1, 1. So let's do this again. Oh, sorry. Yeah. So if we calculate the output of this circuit, then usually you do is you put this in block. So you start you look at different time slice. So we start with the 0, 0, and here, then the 0 hit headma, then 0 becomes 0 plus 1. So we can be a bit lazy. I forgot normalization for now. 0 plus 1, 0, so this tensor 0, so this is 0, 0 plus 1, 0. And then this C naught will add the first register to the second register. And then you go to C naught, so 0, 0 still stays 0, 0. And 1, 0, this 1 added down this 0 become 1, 1. So our result is 0 plus 1, 1. And you normalize it, so it's actually 1 over square root to 0, 0 plus 1, 1. Okay. So usually that's how you calculate the output of a circuit. And then we have a more complicated example, and we can do this even algebraically. So we find that a lot of time you can think about the input as a standard basis state, and then if there's no headma, then really you stay in standard basis state, and then everything can be written out very nicely in this algebraic way. So we have ABC here, then this C naught will add the first register to the second register, so it becomes A, B plus A, C, and another C naught will add the second register to the third register, so it will become A, B plus A, and then C plus this B plus A, so it's actually A plus B plus C. And finally you get Z on here, then you will get minus 1 to the whatever on the first register, so it's minus 1 to the A, etc. Yeah, and then in the midterm we had another example, I think. is related to, so for example, in the midterm, we also have the example where we have a control z. Okay. So I think we did this, right? Z and control z or x. I think it's actually x. But anyway, so say you have x here and you do control z, and you can also think about you put the ABC here. And so ABC goes through this x will become basically a plus 1 and b and c. And and then you go through control z, and it will give you -1 to all three registers multiplying together. So a plus 1 times b times c, and your a plus 1 b c, etc. Okay. So that's a bit of an example of how you calculate circuit. And then now we go to this for final part. Okay. For final part, then we have the phase kickback and this head modulus. Okay. Remember we were talking about this. Okay, but we can go here. Okay. Phase kickback. So phase kickback, we look at this in Oracle model. Okay. So the second part of class, we look at a lot of algorithms in this Oracle model. And remember, this Oracle will encode this small f. Small f can be very different, many different things, but a lot of time we think about small f as a Boolean function. Okay. So it's some small bit string to and map to 1 bit output. Okay. And so a Boolean function, and then standard and okay, then the notation is a bit confusing. I think I should use tilde here. Okay. That's because that's what we use. Okay. So the standard one we actually write tilde. So standard OF it says it reads some x and will write f of x to the second register. And so that's Oracle. We're seeing a lot of Oracle. We're seeing Oracle in Grover's algorithm. But this is not the Oracle we actually use when we do Grover's algorithm, if you remember. So what we do a lot of time is we will do phase kickback on the Oracle. Okay. So what we do is on the second register, we put a minus sign here. Okay. And so the minus state. Okay. So minus state equal to 0 plus 1. Sorry, 0 minus 1. Okay. 0 minus 1. And then you think about you add, so if you add f of x here, and then it goes to still 0 minus 1, if f of x equal to 0, because you add 0, then nothing changed here. And then if f of x equal to 1, then 0 plus 1 become 1, and 1 plus 0 becomes 0. Okay. F of x equal to 1. Okay. And but this is so this is minus to the 0 minus 1. Okay. So it is still proportional to this minus state. So kind of we can think about the minus state stay the same, but you get the HR phase here. So you get the HR minus sign phase here. So you see that whenever the f of x equals 0, you get a minus 1. You get a minus sign. So the end result of putting the minus state here is you get a minus 1 to the f. I should say minus 1 to the f of x, right? Minus 1 to the f of x phase here. Okay. So we can kind of encode all the information about the Oracle on the phase here. That was a little confusing, but a little imprecise because you lose a bit of information here, but almost all information of a small f is encoded in the phase here now. Okay. We lose the information of whether they are all 0 or 1. Okay. But anyway, so we use this phase kickback, and we are able to do a lot of algorithms. For example, the Dirichlet's algorithm and Simon's algorithm, etc. And a good thing to remember in our calculation is this head modulus it's a bit like quantum Fourier transform. But anyway, so sigma to the n, if you think about sigma to the n, apply on an NB string, and what happened is, well, it's an NB string, but it's a computational base state. So it's an NB computational basis state, this is X, and so no matter what this computational basis state is, so it can be O0 or O1, etc. And so no matter what this is, you will get an equal superposition of every possible computational basis state. So this y is from 0 to the minus 1. So y is, here we are using some mapping between NB string and NB string and number. So I guess I should really say y equal to some y 0, 1 to n. So y is also NB string, and x is NB string, and so you sum over all possible y, and then normalize a little bit, and but interesting part is now you get this phase. So the information about x is turned into this phase. You have -1 to the x dot y here, where this dot is you think about inner product. So you have n bit here and n bit here, and you take the like n-dimensional inner product here, and this is amount 2. Okay, so this is the inner product. This is n-dimensional inner product amount 2. Okay, so that's sigma to the n, something nice to remember. Then okay, so that's the basic about the algorithms. And then we talk about quantum Fourier transform and Schwartz algorithm. Okay, so what's quantum Fourier transform? This is quantum Fourier transform. Okay. So quantum Fourier transform, you can think about quantum generalization of a classical Fourier transform, but anyway, it's unitary. So it's indexed by this big N. So like n-dimensional space, you do this n-dimensional quantum Fourier transform, big n-dimensional. Okay, so it's n by n unitary here, and j, we think about j is some number from 0 to n minus 1, big N minus 1. Okay, so it's an n-dimensional space, computational basis. And this unitary says it made this computational basis to, once again, so quite like this equals equal superposition of all computational basis state. Okay. And but with this weird phase, e to the 2 pi I jk divided by n. Okay. And you normalize by 1 over square root n. Okay. And this has a lot of nice property. For example, yes, a nice form of its inverse. So if an inverse is just you take a h1 minus sign here. Okay. And also a good property that you use a lot when you calculate the Fourier transform. So for example, how you derive this thing is that you you notice that those coefficients, they adding together, a lot of time they sum to 0. Okay. So for example, if you sum over e to 2 pi jk over n, okay, and so you either fix on j here, so this is a function of j, and you sum over all possible n, all possible k, so k from 0 to n minus 1. Then you find out that if j not equal to 0, then it's, this thing becomes 0, because we think those phases will be equally spaced out point on this unit circle of complex plane. So we think about this complex plane, this is real axis, this is the imaginary axis, and yeah, so if j not equal to 0, so when you sum over k, you are going to sum over equal partition all part on this circle, and by looking at geometry, you think that this equal partition point, they will sum to origin point, which is 0. And but when j equals to 0, then your points don't spread out. J equals 0, then this e to a 2 pi, e to a something is always 0. So you are always summing this point, and then you sum over n times, so you got n here. Okay. And so this is like the orthogonal relationship to in those Fourier transform state or harmonic states. Okay. but I guess this will prove that this is unitary, etc. And okay, so that's about quantum Fourier transform. Any questions so far? Okay, not. And then using quantum Fourier transform, then we can do this phase estimation. This is the basis of Schwarz algorithm. So we can do phase estimation, and what this do is, so this is a really weird algorithm. It's a quantum algorithm that used to solve quantum things, unlike all the previous and later algorithms. So all those oracle algorithms, they kind of solve a problem, classical problem. We think f is a classical function, and you have some big f that's another classical function. We want to solve it. So the only quantum part is now this small f oracle for small f can take superposition input output. But phase estimation is really a quantum algorithm. So it solves this quantum question where you have this quantum gate u, and you are given some eigenstate of u. So this small u to it. So small u is eigenstate of big U with this eigenvalue e to 2 pi phi. And so the eigenvalue must be in this form e to 2 pi phi because u is a unitary. So this must be known one. And so we want to find this phi. Okay. So phi is the phase. Okay. So we have this really two quantum objects, and we want to find this. Well, this phi is a classical value, but it's related to these two quantum objects. Okay. So we are given one copy of this u, and then we are able to do control u, control big U, and then we want to find this phase associated with the eigenvalue here. Okay. And what we do is we can do this circuit here. So we need some precision parameter big T here. Okay. Sorry, small t here. And but for now we kind of ignore the precision. Okay, so we have some precision parameter small t here, and we start with 0 on this small t qubit, and we do Hedema. So here we have the equal superposition of so I should say some k here. So k from k, you have a 2 to the t possible k here. So k from 0 to 2 to the t minus 1. Okay, and so it's an equal superposition of all computational basis state. As we can scroll up a little bit, you can see that from here. So you do Hedema to a t on all 0, then you get equal superposition of everything, and this minus 1 to a 0 inner product with something is always 0. So minus 1 to a 0 is always 1 here. Okay. Oh, and I forgot normalization. So some kk, and you'll be square root 2 to the t here. Okay. And then what we do is we do this weird gate. So it's I guess multi-controlled U. So the supercontrol U says that you do U to the k if you do U to the k if whatever the first register here is k. Okay. Where now we think k as okay, so we are going back and forth between two representations of computational basis state. Okay. So it's a bit confusing, but remember we can always there is always a 1-to-1 correspondence between 0, 1 to the n and 0, 1 to the n minus 1. Okay, so there is a number representation, and there is a bit-string representation. So up here we use a bit-string representation, but here we really need a number representation. So we now think k from 0 to 2 to the minus 1. Okay, 2 to the t minus 1. Sorry. So from 0 to 2 to the t minus 1. And anyway, so we think if the first, so this first register which have a t qubit, if it's some number here, some number k here, then we apply big U k times. So this can be exponential in small t. Okay. But for now, we just assume we can do this. So, so we think about constructing this gate with control big U, then this can cause to the small t number with a small big U here. Okay. But in Shor's algorithm, we say we can do repeated squaring to do this very fast. Okay. But for now, phase estimation, we just assume we can do this. Okay. So you apply U to the K here, and the secondary term you also input with this eigenstate small u we assume we have here. Okay. And so now we look at what here. What's the state after you apply this super control u here? So after you apply the super control u here, you get so first register is some k, and the second register is u, and got apply the big U on its k times. Okay, so each time you apply big U on small u, you get 2 pi I phi. Okay, and if you apply k times, then you get 2 pi I phi to the k. Okay, okay. And so you get 2 pi to the 2 pi I phi to the k. But now again, once again, you see this is like a phase kickback. So the 2 pi to the 2 pi phi to the k, we can write it like before this small u. But really, for the tensor product, you can write a coefficient anywhere. So you can you can write a coefficient, all those coefficients before your small k instead. Okay, that's just a tensor product. You multiply by a scalar, you can multiply anywhere. Okay. So you can multiply it on small k. Okay. So now you see the second register still stay in this small u, just like the phase kickback relation before. This thing before. Okay. So second register you stay in small u, and the first register now you get a lot of phase here. And so what is first register is about k and e to 2 pi I phi k. And tensor second register still small u. And now you look at this thing and you compare to your Fourier transform here. So you see it's very similar. Okay, so we were being too lazy, but you still have this 1 over small, 1 over square root n here. Okay. So yeah, so you see that what you get is a lot like this. So but instead of jk over n, you have phi k here. Okay. Okay. So instead of jk over n, you have phi k here. Then you think, then if you do inverse Fourier transform, then you will get so you will get so phi is equal to j divided by big N, and big N is actually 2 to the t. Okay. So if you do inverse Fourier transform, the major, you will get a j here, right? And so as we know, j equal to so phi. You compare those two things, then phi equal to j divided by big N. So j equal to phi times big N equal to phi times 2 to the t. Okay. This is assuming phi is actually integer multiple of 1 over 2 to the t. Okay, and then we go through. Actually, we didn't quite go through, but we cannot. If phi doesn't have this form exactly, then you will get a similar thing, but with some error. You just need to do a b mod t, and yeah, then there's some error. For now, we assume there's no error, and so what we get is you get phi times 2 to the t here. Yeah. So that's the phase estimation, and so the point of using mod t here is mod t here, then you get more precision on your phi. Okay. So yeah. Okay. Question so far? Not? Okay. So that's phase estimation. We're a little slower, maybe. Oh no, we should have enough time. Yeah, we should have enough time to finish everything first class. Okay. So that's a quantum Fourier transform. Then we find out that you do quantum Fourier transform -1, then you can do phase estimation. And if you can do phase estimation, we find out that we can do filtering using Shor's algorithm. Okay. So here we skip the the classical part of Shor's algorithm, but basically the most mathematical, the hardest part of Shor's algorithm is the problem called the period finding. Okay. So what's period finding? Period finding is that so you given a big N and some small x that's correspond to your big N, then you want to find the smallest r such that x to the r equal to 1. Okay. So I should say smallest. So smallest r possible here is a period of x, I guess with respect to big N. Yeah. So yeah, so this is a hard problem to do classically. So if you get big N and small x, you know this r will exist, but basically what you can do is you keep multiplying x by itself and doing modern, but then you need about but small r can be very big, it can be like order big N, and yeah, then you need to do a lot of multiplication to find this small r. Okay. But quantally we find out there's something very fast you can do is you can do this period finding algorithm basically use phase estimation. Okay. So the period finding algorithm, so there are details about implication. But on the high level, we are basically doing phase estimation on weird unitary u sub x. Okay. This u sub x is a unitary that says you multiply things by x. Okay. So ux acting on some computational basis y will become xy model. Okay. So it is unitary if x is. Yeah, I think it is unitary if x is confined to n. Okay. And actually, I think it's probably unitary, but anyway, yeah. Okay. So we do phase estimation on this multiplication unitary u sub x, and so that's a big U. And but phase estimation we need a small u here. Okay. And small u here, we actually don't know the eigenstate. So we don't have an eigenstate here, exact eigenstate here to put in phase estimation. But the nice thing about phase estimation is you get if you have a linear combination of a different u. So say you use Ci summation Ci ui here as the input. Then on the output you get the phi I with probability Ci squared. Okay, just because everything is linear. So if you have a linear combination of a u here, and you will get a linear combination of a different phi as the output. Okay. And so instead of using eigenstate on the second register, we don't know eigenstate because finding eigenstate you basically need to know R. But we can use equal to some linear combination of eigenstate that is 1. Okay. So what is this 1? Is a computational state 1 eigenstate of ux. Is you can think about how ux apply on 1. So ux apply on 1, then it becomes x, and then apply again, it becomes x squared, and after you apply ux r times, it becomes x to the r, which equal to 1. Okay. So there will be, so you keep applying ux on 1, there will be r different state, 1 to is x to the r minus 1. Okay. Okay. And so from those r state, you can get some linear combination of them. That's the eigenstate of ux, and it's like this. So there are different eigenstates. So and they are indexed by this small s. So s from 0 to r minus 1, and they are basically equal superposition of x to the k. So those x is k is 1 x squared to x to the r minus 1. K equal to 0 is 1, k equal to 1 is x, and k equal to 2 is x squared, etc. Okay, so it's a universal superposition of x. These are different states, but then you put some Fourier phase on them. Okay, and this phase depends on S. So when S equal to 0, it's just a uniform superposition with no phase. And when S equal to 0 to r minus 1, then you get e to the minus 2 pi sk divided by r. So basically you put some omega s to the k here, etc. And omega s is, well, this rth root of 1, etc. Okay? And anyway, so that's the eigenstate to ux. You can check that because ux basically do the cyclic permutation on x to the k. And so you apply ux on us, then you get one of those face off. So you get k to k plus 1, and yeah, so you get hr of this face off. So ux apply on us, you get e to the 2 pi s over r us. Okay, and so you see us is eigenstate of big ux with phase between being this s over r. Okay, so yeah, so this is small s, and small s remember from 1 to r minus 1. And okay, so finally back to R1. So R1 is actually a uniform superposition of all those US. So if you sum them together and normalize by dividing 1 over R, then you get 1. And you can get this thing by checking that, well, they all have component from those 1 to R, x to the R minus 1, right? And so you can check this relationship by using this thing here. So you will see that the k equals 0, basically, so k equals 0 is this thing, and for all the components of k from 1 to r minus 1 is this thing. And yeah, so using this relationship, you can find out that all those US adding together is just this first component. The first component keep adding together, and all other component has those Fourier phases, and they will cancel out. Okay, so 1 is actually a uniform superposition of all those US. Okay, and so when we do phase estimation with the second register being this 1, then we'll get S over R, and with uniformly random because it's uniform, and there are R of them, so uniformly random, which means each one has a probability equal to 1 over R. Okay, so that's how you do phase estimation. So that's how you do period finding in Shor's algorithm. Okay, you do phase estimation on these UX unitary, UX unitary, and we claim that this is efficient because the UX it's a bit complicated, but on high level we say UX. So the UX to the k we can do efficiently because it's a multiplication, and you can get a high level is a lot of multiplication of a very high power by doing repeated squaring. And also this QFT minus 1 can be done very efficiently. There's something we skip here, but QFT minus 1 can be done in poly theta because you can do a phase Fourier transform basically. Okay, so everything can be done very efficiently here. So, and it will be poly log 2 bigger. And that's Shor's algorithm. But anyway, the quantum part of idea is you do phase estimation on this UX, and you find out that you can find some S over R. And then later, then we say that you can draw many S over R, then you will learn R by doing other classical computation. Okay, any question on this review of Shor's algorithm? If not, then let's go to the next algorithm. It's Culver's algorithm. Okay, and Culver's algorithm I think is easier. So I guess I should write what this algorithm actually do, right? So Culver's algorithm, what I do is find market item. So what is a market item is you are given OF, and so it's X such that f of X equal to 0. Oh, sorry, equal to 1. F of X equal to 1. And given OF. So now we back to Oracle world. Okay. Given OF. And OF do things like this. So it's a face version of Oracle because we only need face version. So OF apply on computational state X, it gives you minus 1 to the f of X times X. And given OF, also for the easy version, we say we know number of market items equal to m. Okay. And so that's I guess the global problem. We want to find only one market item. Okay. We want to find x such that f of x equal to 1. And so the idea of Gover's algorithm is you keep doing two reflections and they will become rotation, and you will rotate your starting state to where it should be. And but before talking about rotation, we should talk about which space are we thinking about rotation. So actually think about this two-dimensional space, okay, that are defined by I guess two states. And so one state is the equal superposition of every marked state, so that's called beta. And the other state is phi, that's the equal uniform superposition of everything. So this is like I guess 1 over square root and I. I don't know. I guess that's right. Some x from 0 to minus 1. Okay. Okay. So psi is everything, and then we have beta and alpha here. So beta is equal superposition of every market item, and alpha is equal superposition of every unmarked item. Okay. And so we can do two reflection. One reflection is reflection around this side because we know this side. So we can apply the 2 psi minus I unitary, and it's actually a reflection around this side. Okay, make sure I didn't do this wrong. Correct. Okay, yeah. So if you put psi here and then say psi, and then you put everything on second order side, then you get minus 1. So you reflect around side. And another reflection is this OF. So OF says that if x equals f of x equal to 1, then you get a minus sign. And f of x equal to 0, then you stay the same. So you think about what the OF do on the two-dimensional plane is the alpha component will stay the same, and the beta component get a minus sign. So it is reflected around this alpha line. Okay. And so global algorithm is just you keep doing these two things. You keep reflecting around this and reflecting around that. And then two reflection will be a rotation of twice the angle. So the angle here we call it theta over 2. Then you do two reflection, you do one iteration. One global iteration is you do both of those things, and you will rotate angle by theta. And so you do it a small n time, then you will be at the angle n plus 1/2 theta. Okay. And also we need to count a little bit about the oracle complexity or query complexity. So query complexity only happen here. So here we call the oracle, and here we have no query complexity. But Gover's algorithm is nice is because it's query complexity equal to the time complexity. Because this gate can also be constructed efficiently. Anyway, so back to the geometric picture. So every time you rotate n plus 1/2 theta, okay. And so you want to end at around beta here. So remember, this beta here. This is all the all the marked item. So we think if you rotate our state, so our state start with a very little, is a very little overlap with beta, but we keep rotating. And so we want to rotate our state to somewhere near beta. So if we rotate to near beta and then we measure, then we are very likely to get something beta. Okay, and so we want theta to be about, sorry, we want n theta to be about pi over 2. And also we're starting, and then we can calculate a bit about theta. So what's the theta? Theta, so we can think about here. So this uniform superposition is theta over 2 and go to alpha. Okay, and so I guess the inner product, or so you think about a measure this equal superposition state, then this component on beta is sine squared theta over 2. Okay. So we just do a measure and go to this alpha component, beta component, and this one is sine theta over 2 squared, just by the geometry. Okay, so length square of this part is sine squared theta over 2, and that should be m over big N. So there are n fraction of mark item. There are n mark item in big N, big M item in big N item. Okay, and then you assume m is much smaller than n, and we can do this rough way summation such that so if theta, so if this is small, then theta is also small. So sin theta is about theta, so it's about so this side is about theta over 2 squared, and you move things around, then you see that theta is twice, so it's 2 to here, and then you take a square root, so square root m over n. Okay. So theta is about this, and you want to finish this thing about pi over 2. But we think n is being very large, so we can get rid of 1 over 2 here. So we have n theta about pi over 2, and so we divide things around, and n should be around pi over 4 square root n over n. And this is order square root n over n. So that's how we get the number of the time or query complexity of Gover's algorithm. So yeah, square root n over n, and that's faster than classical algorithm, because classical algorithm need, so once again, classical algorithm need n over n queries. Okay. And yeah, classical algorithm need n over n query, and but also there is a weird issue we keep going back and forth about this. This thing can overshoot. So the algorithm is like you keep doing this, but it's a bit unclear that when you stop. And so when you stop is you need to know precisely where you are. So you basically know that's about Gover's algorithm. And I think we are 5 minutes early, but I think we can stop here. So any question? Otherwise, oh, here, please.
Will RSA be on exam?
So, what?
RSA?
Excuse me? Will RSA be in exam? I think not, because it's the video one, yeah. Okay. Yeah. Any other question? I guess I should really say maybe, yeah, it's a video one, so so I guess I can say this. Yeah. Any other question? Not, then I think we can stop early, and yeah, let you prepare for the exam. Okay. Okay.